So talking a little bit more about solutions, before we get into some calculations, we've got a few more words to describe solutions. So solutions we could talk about in terms of how concentrated or dilute they are. We could talk about them in terms of if they are saturated, unsaturated, or supersaturated. So to get off the bat here, solubility is a physical property. It is a definition, it's a numeric value, so it's a quantitative physical property that basically sets a limit on how much of something can dissolve in a particular solvent at a given temperature. And so most of the time it's given in units of grams per milliliter. So many grams of salt will dissolve in a milliliter of water at say 25 degrees. And this is something that, like I say, it's a physical property, much like density is. It's also a quantitative physical property. So down here we have kind of the gradation from unsaturated to supersaturated. We could talk about also there's a bit of a gradation from dilute down through to concentrated. And that doesn't totally correlate with these other words. So if we were to talk about something that's unsaturated, it means that it has less than the maximum amount of solute that this concept of solubility is defining. So you could put more sugar in the water, right? Or more salt in the water. So when you have an unsaturated solution, you know because you don't have any undissolved solute present. If I move up and I make a saturated solution, you're going to be making saturated solutions in the lab. Saturated solutions have the maximum amount of solute that a solvent can hold. And so when you get a saturated solution, you're going to know that you've hit that maximum, right? That number of solubility, because there'll still be some undissolved solute present at the bottom of your test tube or jar or bottle or whatever it is. Supersaturated, somehow, and I'll say why in a minute, somehow you can convince a solvent to hold more solute than the solubility number defines. And you can do that by changing the temperature. Up here it says at a given temperature. So if you increase the temperature, you can increase that concept of solubility. Now, you can increase it. Now, when you cool it down, things could come back out of solution. But if you're very, very, very careful, you can keep a supersaturated solution in an aqueous or in a solution form. It won't recrystallize. Now, this is kind of cool, and it really is, how rock candy gets made. Or another application is the instant hot and cold packs. So you can check it out. This is a cool video also on the Moodle site. And really, this is what we're saying. So how can you make a supersaturated solution? If you put some solute in a solvent at a higher temperature, you can get enough solute in the solvent that it is supersaturated. Now you have to cool it very carefully without disturbing it. As soon as you disturb it, if it's unstable, the solute's going to come out of solution, so it's going to recrystallize. If the solution is disturbed, either by clicking a little button or adding more solute or somehow hitting, if you think of the heat pads, like so hot packs and cold packs, the ones that you kind of hit to activate, they're using a supersaturated solution. Some of them, the recrystallization process is exothermic, so that makes it warm as the solution recrystallizes, or if that recrystallization process, that physical change is endothermic, those are going to be the cold packs that you smack to activate. So oftentimes you can recharge these by boiling them and remaking or reestablishing that supersaturated solution. So kind of a cool application, and it really does depend on this physical property of solubility. The rate of dissolving, or how fast you can make something dissolve, it really does depend again on the temperatures the stirring or the agitation or the surface area of that solute. So there's a bit of a caveat as well about gases. Gases are opposite to what is listed here. So let's read through them and then we'll talk about gases in water. Okay, so if I want to dissolve something faster, I could heat the thing up. That makes sense, right? The reason why that works is the solvent molecules on a molecular level, they're moving faster. There's more kinetic energy, and it's easier for them to break up that solute into its dissolved form. Stirring the solution, so agitating it, also gives more energy and helps the solvent break apart the solute more quickly. Making the sugar ground finer or the salt in a finer grind is going to expose more surface area of the solvent, so it's easier for the solvent to break it down and it would dissolve more quickly. So the opposite is true for gases. If you think about gases and how you can keep them dissolved or not, think about uh, warm pop. So these are opposite. If you warm it up, if you increase the temperature, you're going to decrease the solubility. You get flat pop when it gets warm. The other one is if you increase the stirring, right? Everybody knows if you shake it, you're going to have that gas come out of solution, and so you decrease the solubility. Oops, I've crossed too many L's there. So just a little bit of a caveat that gases actually act opposite when they are the solute in the solvent. Okay, so let's test our understanding. So circle all the statements below that are true. If I heat and stir something, that will increase the rate of dissolving of salt in water. That's true. That's what we just talked about, stirring, heating, or grinding it finer. A hot cup of tea can be sweeter than a cold cup of tea. That's true. You're going to increase the solubility of the sugar in the hot, right? That increases how much you can dissolve in the tea. Okay, a cup of cold water will contain more oxygen than a cup of boiling water. Well, that's true. You know, that's an example of how gases dissolved in water, solutions of, say, carbon dioxide in water or pop would be opposite to the other solutions we just talked about. Adding a few granules of sugar to a cup of coffee would make a saturated solution. Well, no, it wouldn't, right? Because it would make a dilute solution. There certainly wouldn't be more sugar at the bottom, which is what was defining a saturated solution. E says more sodium chloride will dissolve in vegetable oil if the container is shaken. So think about that for a minute. This would be an ionic compound in a polar solvent. So shaking it is usually good, but these are insoluble. So that is also going to be a problem. It's not a true statement. The last one says here, more sugar will dissolve in hot olive oil than in cold olive oil. So we'd have a polar thing trying to dissolve in a non-polar solvent. So again, yeah, when you heat things up, you can get more to dissolve, but if they don't dissolve in the first place, then that makes that statement not true. So here's one more application just to kind of test your understanding, and then we're going to get into some math and some numbers. A student dislikes the taste of the tap water in her apartment. She's read that you can that dissolved calcium and magnesium salts usually cause water to taste bad. She also heard that you can purify your water by boiling it. So she decides to boil it to improve the taste. Do you think she will be happy with her results of the boiling water? Why or why not? And what solutes can be removed and what cannot be removed by the boiling water? So think about it for a minute. As a disclaimer, she is not going to be happy, but we have the keys and the science to understand why. So basically what she's going to do is concentrate the things dissolved in her water. So specifically, she's going to concentrate those calcium and magnesium salts. And all we mean by that is that we have an ionic compound with calcium or magnesium as the cation. What she could remove from solution is if she had any gases would come out of solution. If she did want to purify her water, the kind of workaround here, and this is way more fun when we can actually talk about it, but I'm just giving you the answers. If she were to capture the steam, that would be distillation. And that would result in pure water, which would probably make her happy. Although other people argue that it's the dissolved salts that actually, or the minerals that add to the taste of water. Okay, so let's get into some math. So there is a way of calculating or quantifying the concentration or the composition of a solution. And the first way that we're going to talk about it is mass percent. This is not the most common way. It is a way that you'll notice in like hydrogen peroxide was a 3% solution if you look under your medicine cabinet. So it is a way of talking about concentration, but it's probably more prevalent in an applied sense and more in the biology world. So the symbol for mass percent or mass percent concentration is an M over an M and a percent. Now the reason it's an M over an M is to calculate the mass percent is the mass of the stuff dissolved in the mass of the total solution. And remember, the solution is made up partially of the stuff dissolved and also of the solvent that is doing the dissolving. So here we have a few examples. We're also going to see how we could roll this into dimensional analysis. So this one says a sample of seawater has a mass of 135 grams and it's evaporated to dryness, leaving 4.73 grams of salt. Calculate the concentration in mass percent of that original seawater. So mass percent would equal the mass of the solute. So in this case, it's the mass of the salt divided by the mass of the entire sample, right? The whole solution, solvent and solute, times 100. So if I crunch the numbers, I'm going to correct this to 3 sig figs or 3.50%. So that's a 3.5% salt solution. That's what we'd say the seawater is. We have another one to do here. Pretty straightforward to do. Okay, so a solution's prepared by putting 5 grams of salt into 250 grams of water. So the mass percent solution would be the 5 grams of salt in that 250 gram solution. So the mass of the whole solution would be 5.0 plus 250. That's usually the wrinkle. People sometimes miss it. It's really not that tricky, but it can catch you off guard. So if I use my calculator for that, I would say that that's a 2% salt solution that I just made. So in these ones, that mass percent can also be kind of useful if it's written as a unit factor. So I like doing this. It's not necessary. If I were to assume a 100-gram sample, I could turn that percent into a gram. So a 5% solution, if I had a 100-gram sample, means that I have 5 grams of NaF, or sodium fluoride, in 100 grams of the solution. And so if we were to think about what this question says, indicate the mass of the solute and the mass of the solvent, well, I could take the 100 minus the 5, right, to calculate the mass of the solvent, right? That's how much water is making up that entire solution. And so that gives me 95.0. grams of the water, assuming it's water. So same one here, if we have a 25% solution, if it's a 100-gram sample, I could say that's 25 grams of glucose in 100 grams of solution, right? I could see that's how I could do it as a unit factor, right? And it's also gives me the information. Oops, I forgot my sig figs. To calculate how many grams are the solvent. And so that's 75 grams are solvent. So really that question's just asking you about these two components, the solute and the solvent, but that mass percent can be used in this way to kind of give you more information about the solution. So here we have one more using this concept of mass percent, and I'm going to use that mass percent as a unit factor. So what I was writing before is that a 2.50 grams of KCl in 100 grams solution, right? That was using this as a unit factor. So let's take a look at this. We want to know what mass of solute is required to prepare 150 grams of solution. So I'm going to start with 150 grams of solution and then check out how I can use my unit factor of mass percent to figure out what this question is asking for. So if I use my dimensional analysis, it's grams of solution are gone, and I would have this in grams of potassium chloride. And that allows me to crunch my numbers and do the math, and it allows me to then say it's, shoot, where am I? Oh, 3.75 grams of KCl. There is an alternate way of doing this, and I'll just scribble it down below. It might be the way that you work better. So we had an equation as well, right? So you could sub into the equation and solve. So I like the unit factors because sometimes I don't know the strategy to solving these things or the algebra. So 2.5% is my mass percent. I don't know how many grams of solution, but it's in 150 and it's times 100. So if you want to use the algebra, sub in and solve, you totally could. I like that idea of mass percent as a unit factor. Again, going back to that problem solving strategy that can be useful when you get different kinds of questions. So that's mass percent.